Okay, so in this video, we're going to go ahead and work out problems 3 and 4 off the practice. We have a diagram. It says a beam of ions. An ion is a positive or negatively charged atom, an atom that's gained or lost an electron, each with a mass of 1.16 times 10 to the negative 26 kilograms and a charge of 1 e and traveling at 1,850 meters per second. Enters a uniform magnetic field directed into the page as shown. The beam exits the magnetic field in a direction perpendicular to its original direction. While in the field, the beam travels a distance of 3.50 centimeters. What is the magnitude of the magnetic field? Are the ions positively or negatively charged? Well, let's address the positive or negatively charged question first. We can see that if we think of here's our particle, that the velocity is to the right, and the magnetic field is directed directly into the page. So if we point our right hand to the right and we curl it into the page, we can see that the force would be directed straight up on a positive charge. But clearly in this picture, this particle that enters right here, traveling this way, has a force that's pushing it down. So the answer to the charge question is they must be negatively charged. All right, so let's go and see if we can finish the rest of the question. How big a magnetic field do we have? Let's write down all of our given information. We know the particles each have a mass of 1.16 times 10 to the negative 26 kilograms. They have a charge that's 1e, or 1.60 times 10 to the negative 19 coulombs. Since they're negatively charged, they've obviously gained. These are ions that have picked up an extra electron somehow. The velocity of the particle, 1,850 meters per second. All right. While it's in the field, it travels this distance. Well, what does a charged particle do when it's traveling in a magnetic field? It travels in a circle. And since we can see that it exits perpendicular to the direction it entered, while it was in the field, this distance must be 1/4 of the circumference. So they're essentially telling me 1/4 of the circumference is 3.50 centimeters, which means the circumference has to be multiplied by 4. It's going to be 14 centimeters. Now, what we're really interested in is the radius. To get the radius, you take the circumference, and I'm going to go ahead and do the circumference in meters, 0.14 meters, and you have to divide that by 2 pi. That's going to give us the radius. So 0.14 divided by 2 pi. I get that I have a radius of 0.2199. So I'm really close to 0.220. We are going to have 3 significant digits in our final answer, but we'll keep the 0.2199 for now. The formula that we need, since we know that it's traveling in a circle, is the fact that the radius it travels is mv over qb. So in this case, we're solving for b. B would equal mv over qr. So we just fill in all of our quantities, 1.16 times 10 to the negative 26, 1,850 meters per second, 1.6 times 10 to the negative 19 coulombs of charge, and 0.2199. If you want to, you can look at your calculator and carry a little more. 1, 1. I mean, I think we're good. It's a lot of places. And let's solve for B, and we'll round it to 3 significant digits. Let's see, 1.16 times 10 to the negative 26, 1850 divided by 1.6 times 10 to the negative 19, and 0.219911. That came out to that B was 6.099, or to 3 significant digits, 6.10 Tesla. Oops, I left off the times 10 to the negative 4. 6.10 times 10 to the negative 4 Tesla. So we answered both those without too much trouble. All right, we've got one more problem. Following forces, 2 long, straight, parallel conductors are separated by 10 centimeters. The upper conductor has a current of 20 amps to the right, so let's draw that because I think that will help us. 20 amps to the right, and I do not need this. Put it way down here somewhere. And let's see, the lower conductor has a current of 45 amps also to the right. This distance that separates them from center to center here is 10 centimeters. What is the force per unit length between the 2 conductors? Is it attractive or repulsive? Well, our formula for force per unit length is going to be, let's see, mu naught I prime over 2 pi r. Now I feel like I want to look at a formula chart and not trust my memory. So let me double check. Believe that's correct. And that is correct. So we've got that force per unit length. We just have to plug in all of our quantities. That's 4 pi times 10 to the negative 7. 20 times 45. 2 pi. The distance between them is 10 centimeters, so 0.10. If I put all of that into my calculator, I get that force per unit length is 0.0018 newtons per meter, and it is attractive. It's attractive because the current is flowing in the same direction. So that's the answer to A. B says, what is the magnitude of the magnetic field at a point midway between the 2 wires? What is the direction of the magnetic field at the midway point? Well, to calculate a magnetic field due to a single wire, let's do B1. It's mu naught I over 2 pi r. So if we're interested in the magnitude of the magnetic field at the center, so we'll pick a point right here. There's the center. You can see that it is 5 centimeters away from the upper wire. We can also picture grabbing that wire. If I grab that top wire with my right hand so that my thumb points this direction, my fingers are going to be on this side and then they're going to curl around like this. So we can see that right at that point, the magnetic field due to this upper wire is going to be directed into the page. So that's going to be into the page. So we put in all of our numbers. 4 pi times 10 to the negative 7, 20 amps, 2 pi, 0.05, comes out to be 8.0 times 10 to the negative 5 Tesla. And we need a direction that's into the page. Okay, now we have two. We want the magnetic field at that point, but there's two wires exerting a magnetic field. Picture grabbing the lower one. Same thing, our thumb's going to point that way, so we have our hand back there, and we're going to grab it with our fingers like this. Okay, you can see at this point the magnetic field due to the bottom wire is going to be coming out of the board. So this one was into board, this one's going to be out of the board. It's also going to be stronger because it's got a larger current flowing through it. So the total appears like it's going to have to be out of the board. But you can see your fingers are coming out of the page in that picture at that midpoint. So we put in our numbers. 4 pi times 10 to the negative 7, 45. Only thing that changed was the current. And when we do that, we get a magnetic field of 1.8 times 10 to the negative 4 Tesla. This time it's out of the page. When they go in opposite directions, remember these are vector quantities we subtract. If I do 1.8 times 10 to the negative 4 minus 8 times 10 to the negative 5, I can see that that difference, the answer to the question, is going to be 1.0 times 10 to the negative 4 Teslas out of the page. I just did the 1.8 times 10 to the negative 4 minus the 8 times 10 to the negative 5. All right, let's look at C. C says if the current in the lower conductor is reversed so that it is now 45 amps to the left, does the force between the wires change? If so, how? Well, the magnitude will be exactly the same. All the numbers will be the same. So the answer there would be same magnitude, but now it's going to be repulsive because they're in opposite directions. Whoops. Here we are. So the only change when we reverse where the current goes the opposite direction, for as far as the force, the magnitude of the force per unit length is exactly the same. All the numbers are exactly the same. When they're in opposite directions, it will be repulsive. D says, if the direction of the lower conductor is reversed so that it is now 45 amps to the left, what is the magnitude and direction of the magnetic field at the midway point? Okay, let's stop and think. It won't change anything about B1. Let's pick a different color. B1 is still going to be 8 times 10 to the negative 5 into the page. But if I have the current going this way, when I grab it with my hand now, I'm going to be grabbing it like this, whoops, like this, my right hand, My fingers are going to be on this side now. Whoops, that doesn't look very good, but you get the idea. When I grab it, so now this is going to be going into the page, just like this one went into the page. So by reversing that current, whoops, this 1.8 times 10 to the negative 4 Tesla now goes into the page. So when we do part D, they're both going into the page. I'm going to have to add those up. 8 times 10 to the negative 5 plus 1.8 times 10 to the negative 4. So instead of a difference, because they were in opposite directions, it's a sum, they're in the same direction. The correct answer is going to be 2.6 times 10 to the negative 4 Tesla into the page. The nice part is we didn't have to do much in terms of calculations. These individual magnetic fields have the same strength regardless of direction. We just have to look at the directions. When they went in the same direction, we actually, in the middle there, ended up having to subtract. When they went in opposite directions, they both were pointing into the page, so we had to add them together. Okay, that finishes our solutions to problems 3 and 4.